Well, welcome back. And this is Lab 1A, but now the RStudio portion. And all the labs run rather parallel. Whatever analysis we're doing it in both SPSS and R so that you can compare the results to each other, kind of get used to both the coding and the output from both these types of analysis software so that you start getting used to what the output look like. So getting started, we're in the modules for Canvas, and that's where you'll find your materials for the RStudio portion of Lab 1A. So you'll need the R script. You want to download that and put it in your working directory that you made for RStudio. And you'll also need the data set, which is a CSV. From there, you're going to open RStudio and open your R script. So it's called Lab 1A. And it's long, but a lot of that is because I put a lot of commentary in there. I always start with a title for your lab, for the script, what the goals are. I find that's helpful because it keeps me focused on the analysis that I'm trying to do with that work time I'm using in R. And what you'll need to get started with this lab is reviewing the Denellen article for the mini IP scales, having the CSV file, and you typically want to go ahead and make sure any packages you're expecting to use are installed. So I'm going to run this by holding Command Return because that's how I can run it from the script window, the script panel. And I know R is ready for me because I have this command prompt when it's done working. So I'll get the stop symbol while it's working and the command prompt when it's ready. And I'm going to go ahead and load tidyverse. So the first thing we need to do is read in the data, and that can be tricky sometimes, especially once you get better in working with R and coding. You know how to run the analysis, but if you can't get the data into R, how do you run the analysis? So we're going to try different ways of reading in data as we go through different labs, and so that you have lots of opportunities to look at different ways to get data into RStudio. So what we're going to use here is, it's called Reader. So the package is called Reader and can be used to read in several different types. What we're going to use, so I'm saying name a new thing in the environment called Lab 1A. It's assigned by this function, read_CSV, and this is the name of that file in my working directory. So as long as the thing you're looking for, as long as the file you're looking for is in your working directory, you don't need a whole path. You don't need to show R a whole path. It's going to look here first in your working directory. If you're having it look someplace else, then you're going to have to give it a whole path to use. Running that code, now I have 28 observations of 25 variables in the environment called Lab 1A. When I fold down, I can see that it thinks every single variable is a numerical, which is not the case. Case ID should be nominal, year should be, all of these should be factors because they're categorical. So I need to make some changes there, right? So the first thing we're going to do is change the case ID variable to a character. So Lab 1A case ID So it's this data set. The $sign represents this is a variable. So data, then variable, assigned by, using the function change it to a character. Change what to a character? This variable in this data set. So basically, I'm overwriting the variable. I'm changing that variable itself. And if you watch this indicator of numerical, when I run the code, now it changes to character. So next, I'm going to tell R which variables are categorical variables, or called factors, and what those levels are. Remember, year had to do with college year. They weren't 4, 3, and 2. They were senior, junior, sophomore, right? In fact, to adjust the college variable, we've seen in the CSV or in SPSS that there were no freshmen. And because R only sees what's there, and it goes in order, it names 1 first, 2 second, 3 third, and so on. It's going to go either in numerical or alphabetical order to the information that's in there. So we need to be mindful of when there is no one in category 1. There's no freshman. So also, instead of overwriting this time, let's create a new variable. That way we're able to compare between the old one and the new one and make sure that the coding was correct. So let me grab that one. What does this say? Well, it says to make a new variable called year.f, assigned by, it's going to be a factor type using the variable called year in that data set, and give it labels of the first one is going to be called sophomore, the second one junior, the third one senior. And this is because we had no freshmen in the data set. So running this, now at the bottom we have year.f factor with 3 levels. Now we're going to use our select tool and be able to compare these two, both the old year variable and the year.f variable. So here's the year data, the variable called year, and the variable called year.f. So when there was a 4, it's now called senior. When it was a 3, it's called junior. When it was a 2, it's called sophomore. Good. That's exactly what we wanted. For ethnicity, there's 4 levels. So now we need a new variable. And again, I don't want to overwrite. I want to make a new one. But 1 is Caucasian, 2 is African American, 3 is Native American, and 4 is multi-ethnic. So here, I'm going to do pretty much the same thing, but with more levels. Let me pull this out so we can see the whole thing. So ethnicity, and it didn't matter that I used a dot. I can use a dot in the variable name. I just call it .f so that I'm reminded that that's a factor. You can call it whatever you like. And then there's the function creating a factor of this variable, but now using these labels. And when I run that, it adds it to the bottom. And you can see it changing that now it's got 27 variables instead of the 25 we started with. So I still need to make gender. And then I have now 28 variables. So now that's all of the categorical variables I needed, but let me put them up to the front so that they are where I can see them more clearly. And this is using the slick tool that we learned about in our orientation. It says, right back onto Lab 1A, selecting the year factor, the ethnicity factor, and the gender factor variables, and then everything else, all the other variables can come after it. And that's important because if I don't include that everything, it'll drop them. It'll drop them off, and I'll have to start over by reading in the data set again. So now, when I look at this, I have those 3 that I made first, and then everything else. Okay, so that's what I needed to get my read-in data and everything with the correct measurement type. So I have my categorical variables, everything else is numerical anyway, and I changed my case ID to a character because it's just a nominal, it's not even a factor. So my next task is to compute the variables. And the first variable we're going to compute is the age of the participant by subtracting their birth year, which is what was asked in the survey, from the year 2018, which is the year the data were collected. So to compute that, we're just going to make a new variable called age. So I want to add a variable called age to Lab 1A, and it's going to be assigned by 2018 minus the year of birth. And then I'm up to 29 variables, and age is at the bottom there. So now we need to do all that reverse coding, because the big 5, the subfacets for big 5, some of those items are reverse coded, which is what we know from looking at the Donnellan paper, that items 6 through 10 and 15 through 20 need to be reverse coded before we can make those subfacets for each of the big 5. So let's start by working with IP6. This right here, head Lab 1A, when I run that, it gives me the header. It gives me the header of all of these variables in the data set. It doesn't go very far because of how wide this is, right? But it does show me IP6, and that the first few numbers here are 32143. And after that, I'm going to run this. So this says, take this data set, Lab 1A, then this is our pipe function, then use the function mutate on IP6 such that you're going to recode what? IP6 with the following information. And notice there's backticks for each of the 1, 2, 3, 4, 5 right there at the beginning, but not on what it becomes. And the backtick is on my keyboard beside the 1, like just to the left of the number 1. Then I'm saying to give me the header again. So I'm going to run this. And now IP6 is 34523, right? And that's exactly what we would expect with the reverse coding. 3 becomes a 3, 2 becomes a 4, 1 becomes a 5, 4 becomes a 2, 3 becomes a 3. So good to know it worked, right? And that was just one of them, though. So what I would want to do is run more than one variable at a time. And as long as the variables are sequential, like 6, 7, 8, 9, 10, like that, we can use the colon to indicate the columns that are sequential. So let's take a look at this. So this says take the dataset lab 1A, then mutate across 6 to 10. Argument 1 here says to pass these columns right here, pass these columns through a recode. Argument 2, for each column, use this information to recode it. And then again, head just means give me a header of the new information. So now 6 through 10 are recoded. Like here's IP7, it starts with 1 and 2. And if I go back to before, when we called it, we can call up the lab itself. Like if I open it here and we go down to 7, I don't see it done. 1, 2, 1, 2, 2. It should be the other way. Let's see what's going on. Okay. 5, 4, 5, 4, 4 for number 7. 1, 2, 1, 2, 2. 5, 4, 5, 4, 4. Notice that we haven't actually changed the real data set. We're just recoding, and that's what's showing in the console. So that's our next thing we need to do. We need to recode 15 through 20 because those also need to be reverse coded, and we need to save this information, this recoding, to the data frame itself. Let's do that. So everything we've done so far is only changing it in the console down here. It's not actually changing it in the data set, but we're going to do that different. Here we're going to kind of up the version. I'm going to give it a new name, so it's going to be a new object, and I'm saying I want a new thing called lab1a.2, and it's going to be assigned by this data, lab1a, through which, or then, mutating across 6 through 10 with this recode, and then also across 15 through 20 with the same recode. So we'll run this, and now we have a new item in the environment called lab1a.2, and we can compare. Let's get a couple of variables and compare them just to confirm what's going on. This says using lab1a, so the original IP10, give me the header, and lab1a.2, so the second one with the recoding, give me the header for IP10. That's one of the ones we recoded. Same thing for 15, another one that we recoded. So running both of those. For 10, anything that was a 2 is now a 4. 1 is 5, 1 is 5, 1 is 5, 1 is 5, 2 is 4. Good. 4 is 2, 1 is 5, 2 is 4, 3 is 3, 1 is 5, 2 is 4. Awesome. So it looks like we're cool with the recode there, the reverse coding for those items. And we have the new data set to work with the recoded items. And keep in mind, this was an overwrite. This was not a new variable. We overwrote those items, 6 through 10 and 15 through 20. If we want the old ones, we got to go to lab 1A. But the new ones reverse coded are lab 1A.2. But now we're ready to compute the skill level variables. And again, using Denellen to look at which variables comprise each subfacet. So here are the items that should be in neuroticism, extroversion, openness, agreeableness, conscientiousness. And remember, since we overwrote, we don't have the R's. Like we don't have 9R or 19R. We just have 4, 9, 14, and 19 that would go into neuroticism. So let's play with extroversion, since that's the one that we know what the items are. So take lab 1A.2 data frame and then mutate a new variable called ext, which is going to use row means. That's a new function. We're getting the mean across the rows, selecting the aforementioned data frame. That's what that period is. Select the data frame that we already told you about and the following columns: 1, 6, 11, and 16. And then go ahead and give me the header row. So here it's the header row. You notice that I can't see extroversion because it's too far away, right? But I can see it down here, that extroversion was created now, and it's at the end of the data set. But again, we didn't make changes to the actual data set, right? It's not here. It's only here in the console at this time. So now we need to create all 5 subfacets and keep the new variables in an updated data frame. So each time I'm wanting to update the data frame with what I want. So to get these, this is what I want to do. I want to make a new I'm going to up the version. I want lab 1A.3, which is going to use the one with the reverse coding, the data frame with the reverse coding, and then mutate each one of these. And now I have O, C, E, A, and N, and each of what goes into them, right? According to Denellen. Each of the items that should be part of each of those subfacets. So running that, now I have a new item in the data, in the environment. And if I come up here and scroll all the way to the end, there's my new data, my new variables, which are the means of those items that we told it to use for each of those subfacets. All right, so now we're at a point where we have all of the study variables ready to start analyzing, ready to do descriptives on or inferential tests, things like that. But it would be helpful to kind of downsize this a little bit so that I'm not having to scroll all the way through to find the variables, right? So what we'll do here is, using the select tool again, create a subset of the data frame. All we want is case ID, year, ethnicity, the factor ones, and gender factors. We want the continuous variables for age and the big 5 subfacets. So create a new item, a new object in the environment, selecting from that object in the environment, lab 1A3, keep case ID, year factor, ethnicity factor, gender factor, age, and ocean. So now I have a new item. I got 28 observations of 10 variables because that's all I kept. Now we have the data set ready to start really looking at, getting our description of the sample. So similar to what we've looked at before, we need frequencies for the categorical variables and descriptives as far as mean and standard deviation for the continuous variables. And for a general look of a data, I'd say summary does a quick job of it. And that will put it down here in the console for us. So we can see how many sophomore, junior, senior we have, the counts for ethnicity, the counts for gender. We have mean for all of the continuous variables. What do we not have? Well, we don't have percent of the whole, and we could just calculate it. 6 divided by 28 times 100 would give us the percentage of seniors in the whole sample. But we could also ask for the proportion, ask R to give it to us. Similar, we have the mean, but we have min and max, right? Those are good. We have the quartiles, which is like a range as well. And we don't have standard deviation. But again, we can ask R for those. So let's do some of those. For getting proportions. Proportions table of this data set, this variable. So that tells us the proportions in decimal form for that one variable for college year, proportion of sophomore, junior, and senior. And I can also add things, add functions and statements to make it more accessible. I can round to 2 places. Proportions table, and I can go ahead and get it to convert to like a percent level by multiplying by 100. And now we can see what we would more or less report. As you see in sample descriptions, we typically report to 1 decimal place, but I like getting 2 so that I can just see how it's rounding. So write the additional requests for ethnicity and gender. All you have to do is copy one of these and put them in there and change what variable you're looking for. And if you want to get count and percentage together, there is a pretty cool package called Janitor that does a decent job of it. And the way we would use that is with a table. Table of dataset lab 1A.4 of the year factor. And now it's got how many and the percent. You would have to multiply by 100 to get the percent, or see if you can work it into the function there. So again, write the next ones for ethnicity and gender. All you got to do is copy paste and change out the variable there. So now what is left to do? So in R, we're constantly having to think for the machine. It's not going to kind of just give it to you like, okay, this is all you need for writing a sample description. You have to say, okay, what do I need? What do I want out of this? And then ask for the things you want in R. So what do we still need to write the sample description? We still need standard deviation. And for a continuous variable, we can ask for the basics using a summarize statement. Something like this. Summarize this data set, give me something called average, which is going to be the mean of age, the standard deviation, the SD, which is going to be the SD of age, and how many. And that will give me the information right there that I can use for write-up. The average age, standard deviation, and that there were 28. Now this right here, this statement. NA, so not available, missing values, remove or don't consider them, is true. It just means if there are missing values, ignore them. And in any of your continuous type variables, sometimes you'll get an error if there is a missing value that you forgot to ignore. This current data set that we're working with does not have any missing values, but it doesn't hurt to have this statement in there. It still gave us the information we needed. If you don't have it in there and there are missing values, you're going to get an error. So if you're getting a weird error and you're not sure why it's not calculating a continuous for you, it might be because you need this statement somewhere. Also notice that using summarize, we would have to ask for each variable separately, which can be tedious, right? You can still save your script and keep having little tidbits of script that are good that you like using over and over. But let's try to get a table of everything we need. So because we've already reduced the data frame to just the study variables, it's got a few variables that are categorical and it's got a bunch of variables that are numeric. We can ask R to summarize only the things that are numeric and then give us the list of mean and standard deviation, ignoring anything that's missing. So now we have the mean of age. So we got the mean of age, openness, conscientiousness, extroversion, or agreeableness, and neuroticism. And we have the SD for all of those. So that would be handy to have, either writing that down or having it where we can get to it later. It's easy to have it for later by adding it into your environment. I'm just going to take the script, and put it right in front of my statement there. And now I have it right here handy. See what I mean? So now we have all the information we need to do a sample description, to describe the characteristics of the sample. And the files you want to keep from this are this R script with your coding work that you've been working on. And that's it for this first part of our lab in R. Hi. Alrighty. Just finishing up with Lab 1. Lab 1B, we're looking at normal distribution of the continuous variables. So in R, what we'll need is the data set that you created with Lab 1A, so that descriptives data set. And you're also going to need tidyverse and a library called moments. So same thing, we're going to inspect histograms, conduct the test for normality, evaluate skewness and kurtosis, and identify potential outliers. And all the while trying to identify the pieces in the output that help us with the write-up of that information. So we need to keep or remake the Lab 1A data set that you made. You might have to go through your script again to be able to get that in. And it should be 28 observations of 10 variables. Now from this, we're going to make a subset of just the case ID and the continuous variables. We're not going to keep the factors for what we're doing here, because we only want to look at normal distribution on these continuous variables. So I'm going to select from the dataset lab 1a.4 these variables, and I'm going to call that a new thing in the environment, lab 1b. And I kept only 7 of the variables. So looking at the normality of continuous study variables, we want to check out the histogram. We want to look at summary statistics like skewness and kurtosis. We can run a normality check test called Shapiro-Wilks, and we can also check for outliers. So doing our first visual inspection of the histogram is calling for a ggplot. So I want to plot using lab 1b, aesthetics x equals age, and create a histogram with a bin width of 1. And we have that extreme positive skew going on for this one. And that's what you want to say. You want to say a visual inspection of this variable seems like you have a positive skew here. And we can gather other descriptive statistics to find out more about it and report about it. So the Shapiro-Wilks test is in the basic R core basic R installation. Shapiro-Wilks is the Shapiro.test is the function that we're calling for, and then the argument is saying on what variable. This data set, lab 1b, variable age. So coming down here, we see that the estimate was 0.56. The p-value is less than 0.001. And when you're looking at violation tests, if you're looking at assumption violations and it's a test for it, it means that when you have a significant test, that item, that variable, that model, whatever it is, has violated the assumption. This was a test of normality, therefore a significant test shows that this variable violates normality. We also are going to use the moments package to look at skewness and kurtosis. So skewness is coming in at 2.96. So that's pretty high because 0 is what indicates a normal distribution. Anything further away from 0 than plus or minus 1 indicates a highly skewed data. Now kurtosis right here is coming in at 11.17. And kurtosis, a normal distribution baseline, is 3. Some programs are going to subtract that 3 out and make the normal baseline 0. So you just need to watch for it. But greater than 3 means that it's got a high peak, it's really peaky, and doesn't have as much distribution in the tails. Whereas less than 3 is going to be really flat and have like a lot of distribution in the tails and not any kind of peak. And I left you a couple of websites that are handy for looking at and understanding skew and kurtosis better. So we're going to get the remaining code for these histograms for openness, conscientiousness, extroversion, agreeableness, and neuroticism. And what you can do is just go ahead and write your first set of code and then just copy and paste it and replace the variable you need to replace to get those other ones in. And when you run these, I'm leaving the information about what was found so that you can see if your run is matching. Okay, let's check out this. There's a difference between SPSS numbers and R numbers. So here's for age, right? We have Shapiro-Wilk, we have skewness and kurtosis. I'm going to move back over to our output in SPSS where we have skewness at 3.13 and kurtosis at 10.09. So still very skewed, very kurtotic, but not exactly the same as what we're getting in R, right? So 2.9 compared to the 3.1 and 11.2 compared to the 10.1. Still very similar, but not the exact same numbers. But then let's look down here at the test for normality. Shapiro-Wilk statistic was 559, p less than 0.001. And in R, Shapiro-Wilk was 559, p-value less than 0.001. So for Shapiro-Wilk normality test, they seem to be right at exactly the same. But the way they're computing skewness and kurtosis seems to be a little different. And I'm not sure if that's because SPSS is moving it to a 0 kurtosis or not, but they're very similar to each other, so I'm not worried about it. Next, we're going to check on outliers for each of these continuous variables. And it's really easier to see outliers in a box plot. So I can run a box plot like this, box plot of this data set, this variable, and I have this right here. Or I can use ggplot where I say I need a plot using this data set, lab 1b, make me a box plot where x is just x and y is age. So there's that one. Now out of these two, like, you can use whichever one you like. I like that this has the age like label on the side, because once you get a whole bunch of plots, you start wondering like, what was this one for? I don't remember. So it's kind of nice to have the information right there on the plot. And we can, it looks like we have 2 outliers here, right? And there's different ways of identifying the cases that are outliers. For example, we have 2, this is age. We can just view lab 1b. And when we pull that up, we can sort age like ascending and descending. And it looks like we have 2 right there, really high, 45 and 38, right? So those look like they're going to be the outliers. But we can also just poke around and look for what others have created in code that looks interesting. Like even here, it says that 45 and 38 are the values that are the outliers. And if I looked around to see, I left the website of where I found some information. You just poke around, Google search, how do I get outliers on a box plot, and see what others have done. If they start going into stuff that looks super complicated, just look for another option. I found this one where you name to an object, I'm calling it out, that box plot stats, the 45 and 38. And then I'm naming to another object, out ID. I was just giving it a name, it could have been anything, using this function, which out of that data set, lab 1b, the variable age, is within out, the out we just made. So we make out, now that's in the environment. Now making out ID, again, it's just a name I gave it, but it's saying which in this variable is within this out object. And then the out ID is just printing it down here. It says 1 and 11, and that's the case IDs it gives it. It's not our case ID, because ours are 1 and 19. And you'll see in the SPSS output, if you go up to the case number that the system gives it, 1 and 11, and the case ID we gave it, 1 and 19, that's what R is picking up right there. But let's try something else. A box plot labeling the outliers. I'm going to take box plot of this variable. I want a label on the y-axis of age. I want a main label, box plot of age, and I want to put text in there. Let's see what it looks like. So that's kind of cool. That would be nice of a figure that I could help my reader understand what the nature of this variable of age is, what the outliers are, and how that is, what the nature of this variable is in the data set. So we can request box plots for the other continuous variables: openness, conscientiousness, extroversion, agreeableness, and neuroticism. And I left the what you should expect. So here's openness, and there are zero outliers in openness. For conscientiousness, none. For extroversion, none. For agreeableness, there's 1 down there. So I can go back to the data and say, okay, if I sort this, there's lots of 5, 5, 4, just like it shows. It's got all these high numbers, right? But if I sort it descending, you have that 1 data point down there, 1.75, and then it jumps up to 250 before you start having data again, or values. So there's an outlier right down there, case ID 4. And for neuroticism, no outliers. And then it's back to your write-up. Like I said, just letting your reader know that you visually inspected the histograms, that you ran and looked at the skewness and kurtosis and ran a normality test. And just that's all the evidence that you have to convey what you think. You are the subject matter expert. What do you think about that distribution? Because like I mentioned, the tests and skewness and kurtosis, those are very sensitive to the sample size. The larger the sample size, the more likely you're going to get a significant violation on the Shapiro-Wilk test. So look at it, give your expert opinion on if you think it's a normal distribution, if you think it's skewed, and then also give the evidence of the skewness, kurtosis, and normality test. Well, that is it for Lab 1. Hope you enjoyed, and I'll see you in class.